When we left off at the end of the last video, we were looking at this definition of inverse functions. What it means for one function to be the inverse of another, and it is a mutual relationship. They are inverses of each other. But if you have one function that turns out to be the inverse of another, instead of giving it a totally different name, you can just call it f inverse with the little -1 superscript. That's the notation for the inverse of f. If you were calling your function h, and then you had another function that was the inverse of that, you would write it h inverse, h with a little -1 superscript. One example we looked at the end of the last section. When we were talking about function composition, one of the examples we looked at was where f of x was 4x minus 5, and g of x was x plus 5 over 4. And we saw that if you compose those two functions together, f of g of x turned out to just be x, and g of f of x also simplified down to just x. So these two functions are inverses of one another. Instead of calling this blue function g, I could just call it f inverse. Or I could keep calling it g and then call the red function g inverse. And if we drew graphs of these two functions, they do have that kind of relationship where they're reflections across this diagonal line y equals x. For every point on one graph, if you interchange the x and y coordinates, you get a point on the other graph. So to verify or check whether two functions, f and g, are in fact inverses of one another, the way you would do that is look at those function compositions. Check out what g of f of x is and see if it simplifies down to just x. And f of g of x should just equal x for all x in the domains of the two functions. Now, if you check one of these and it works, you can be pretty sure the other one's going to work as well. The only reason it might not is if there are issues with the domain. If it works for part of the domain but not another part. But it's best to check them both. So let's try checking in this example here. Here we have two functions. F of x equals -x cubed plus 2, and g of x equals the cube root of 2 minus x. And we're supposed to verify that these are inverses of one another. So remember how we do that. We check that g of f of x simplifies down to just x, and f of g of x simplifies down to just x. So first of all, how about f of g of x? Remember, f of anything would be negative anything cubed plus 2. So if the anything is g of x, which is the cube root of 2 minus x, then we're looking at negative cube root of 2 minus x cubed plus 2. Well, cubing undoes the cube root. So we have just negative 2 minus x plus 2. The negative applies to the whole thing. Negative 2 and negative minus x, which is the same as plus positive x. And then negative 2 plus x plus 2. Well, the negative 2 and the positive 2 add up to 0. So really this is just x. So that checks out. Let's try it the other way around. G of f of x. Take the formula for g, replace the x with f of x, and it looks like the cube root of 2 minus -x cubed plus 2. So underneath the radical sign, if I remove the parentheses and distribute the minus sign, it's the cube root of 2 plus x cubed minus 2. Well, this 2 minus this 2 kind of cancels out, so it's just the cube root of x cubed. But the cube root undoes the cubing, and that's just x. So that checks out. So yes, they are inverses of one another. They pass the test. And if you look at their graphs, they have that kind of symmetry. We got the red graph And if you reflect that across that diagonal line, you get the blue graph. Now, how do you find the inverse of a function? Say you've got a function, you know it's a one-to-one function, it passes the horizontal line test, so it does have an inverse. How do you figure out what that inverse is? How do you come up with a formula or an equation for it? Well, you normally would write y equals f of x. But if you interchange the variables and write x equals and then f of y, then you can just solve that for y. Get y by itself on one side, and whatever it turns out to be equal to in terms of x, that's your inverse. So here's the way the book describes the procedure, but really it just comes down to write x as a function of y, with y in place of where x used to be, and then use your powers of algebra to solve that for y. And whatever y is equal to, that's the inverse function. So let's try this on an example. Let's find the inverse of f of x equals 8x plus 1. So I'm going to start by writing x as a function of y. X equals 8y plus, I meant to change that to an 8x plus 3. I decided I like that example better. So pretend we're finding the inverse of 8x plus 3. So start by writing x equals 8y plus 3. And now solve that for y. First, I could subtract 3 from both sides so that the y term is by itself, and then go from 8y to just y by dividing both sides by 8. So we get y equals x minus 3 all over 8. So that's the inverse. We can either write it exactly like that, x minus 3 all over 8, or we can break it up into x divided by 8, or x times 1/8, minus 3 divided by 8, or 3/8. So you can write it either way, x minus 3 all over 8, or 1/8 x minus 3/8. Same thing. So that undoes what this function does. And that makes sense. What this function does is whatever number you give it, first it multiplies by 8, and then it adds 3. To undo that process, to reverse that, first you would subtract the 3, and then you would divide by 8. And here's the graph of the original function, 8x plus 3, and what we came up with for the inverse, 1/8 x minus 3/8. And they do look like inverses. How about this one? Find the inverse of f of x equals 1 plus the square root of x plus 3. Now notice with this function, the domain is that x has to be greater than or equal to negative 3, and the range is that y is greater than or equal to 1. You can see that right away on the graph. All the points that make up the graph have x coordinates greater than or equal to negative 3, and y coordinates greater than or equal to 1. But you could also see that from the equation. If we're going to take the square root of x plus 3, x plus 3 needs to be greater than or equal to 0, so x needs to be greater than or equal to negative 3. And then what we get out of that, the square root part has to be 0 or bigger. It can't be negative. And if we take 0 or bigger plus 1, we get something that's 1 or bigger. So that's why the range, what comes out of the function, has to be greater than or equal to 1. So let's work out the inverse. Let's write x as a function of y. X equals 1 plus the square root of y plus 3. Now we got to get that solved for y. So I will start by subtracting 1 on both sides. X minus 1 equals the square root of y plus 3. Now, to get that square root sign out of the way, let me undo it by squaring both sides. X minus 1 squared equals the square root of y plus 3 squared. And when you take x minus 1 and square it, If you multiply that out, remember it's not just x squared minus 1 squared. What it is x squared minus 2 times x times 1 plus 1 squared. So x squared minus 2x plus 1. And then over here, squaring cancels out the square root. The square root squared would just be y plus 3. Okay, one more thing to do to get y by itself, and that would be to subtract 3 on both sides. So y turns out to be equal to x squared minus 2x minus 2. So if we've done everything correctly, that should be the inverse. F inverse equals x squared minus 2x minus 2. Plug a number into f and see what you get out. Like if we plug in, 6. 6 plus 3 is 9, square root of 9 is 3, 1 plus 3 is 4. So plug in 6, we get 4. That means here if we plug in 4, we ought to get 6. 4 squared is 16, minus 2 times 4 is 8, 16 minus 8 is 8, minus 2 is 6. It works. How about the graph? If we compare the graph of f with the graph of f inverse here, it's, wait a minute. It's not just reflected across that diagonal line. Instead, we get this whole parabola here. What's going on here? Well, remember earlier I was talking about domains and ranges and how if you find the inverse of a function, the domain of the inverse is the same set of numbers as the range of the original function. And the range of the inverse matches up with the domain of the original function. So with the function we started with, we were only allowed to plug in numbers that were greater than or equal to -3, and we could only get out numbers that were greater than or equal to 1. So if we're thinking of this as the inverse, the thing that undoes what this function does, we only want it to act on numbers that could have come out of the original function. That is, numbers that are greater than or equal to 1. So the only kinds of numbers that we could have gotten out of f are numbers that are greater than or equal to 1. So if those are the only kinds of numbers that we plug in to f inverse, we make it so that the range of f inverse is everything greater than or equal to -3, and the domain, what we're allowed to plug in for x, is everything greater than or equal to -1. Then we don't get all of these points on the graph. We just get these points. These are the points that have x greater than or equal to 1 and y greater than or equal to -3. But if we just take the points where x is greater than or equal to 1, yeah, that does look like we took the original graph and just reflected it across that diagonal line y equals x. So things can get a little bit subtle when you have a domain and a range that aren't just all real numbers.